Hello everybody. In this video we'll be covering one of the sections in Chapter 2 of our textbook Introductory Chemistry by Tro. This chapter is titled Measurement and Problem Solving. So one of the first things we're going to do is we're going to make a distinction between what we're going to call exact numbers versus measurements. And this is really where the math that you're going to see in a science class like chemistry is going to diverge from a pure mathematics class that you've seen before. Because in pure mathematics, we typically are going to make the assumption that all numbers are exact numbers. They're known with absolute certainty, and they're also dimensionless. They don't have any units associated with them. However, in the real world, where things get a little bit messier and we're making the measurements of things, that's not true. We wind up with these measurement quantities that have uncertainty and have actual units associated with them. And so we have to take special care to make sure that we're representing these measurements in a way that actually reflects how well we know their true value. So the first thing to discuss here is exactly how do you come across an exact number. And there's really two ways that you can know the exact value of a quantity. The most often method is by counting. For instance, if you counted the number of pennies in a pile, you would know with absolute certainty how many pennies there are. The second way is by definition, essentially. So this is where we have just said that this is true. For instance, we've said that 1 ounce is exactly 1/16 of a pound. So we can know for sure that this relationship holds and is true because we said it so. However, whenever you use an instrument to compare the quantity of an object to a standard, there is an uncertainty in the comparison. Okay, so we're never going to know with absolute certainty exactly how much of the object we really have. So measurements are written to indicate the uncertainty in the measurement. The system of writing these measurements we use is called significant figures. So we're going to be able to tell, based on how we wrote the number, how much uncertainty we have in it. When writing measurements, all the digits written are known with exact certainty except the last one, which is an estimate. So we're going to finish off our number with an uncertain value. Okay, so in this case, if we have 45.872, the 45.87 is known with absolute certainty, and this 2 here is an estimate. Okay, this number may not be exactly 2. So if that's true, then when we're making measurements, we need to get an estimate for that last digit. Okay, so for instruments marked with a scale, you get the last digit by estimating between the marks whenever possible. Okay, you would do this by mentally dividing the space into 10 equal spaces, then estimating how many spaces there are between the two measurements. So if we take a look at this, if we're over here in grams, right? This is 0, this is 1 gram, this is 2 grams. I can see that this line is between 1 and 2. I can see that it's closer to 1 than it is to 2. So I can make some kind of estimate of where this is, like say 1.2 grams, all right? Whereas if I had just simply chosen to put 1 gram, I would be further away from the line than what I really can do with this instrument. And when I write it, I will write out 1.2 grams, where the 1 is the certain thing, right? I know that there's at least 1 gram in there, and the 2 is an estimate. That was just me saying I think it's about 1/5 of the way between those two lines. So here's an example where you guys can try this yourselves here. We have this scale here on a thermometer. We're going to note that when we have thermometers often, they'll do this thing where they get to 100 and then they stop writing it out. So this is like actually 110 and this is 120. So if we have 100 here, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings in between, okay, then what we need to do is to count up from here. So if we go 1, 101, 102, 103, and then we need to estimate how far between 103 and 104 this guy is. And when I did it, I got about 103.4. I'm going to say that's just a little bit less than exactly halfway between those two values. So the non-placeholding digits in a reported measurement are called significant figures. So that's any digit that does not, it's not there just simply because you need it there in order to write it using our basic format, okay? So some zeros in a written number are only there to help you locate the decimal place. So really what we're talking about here is just our use of 0 as a placeholder in the number scheme that we've always used. It's something that we've learned since we were little kids, so you may not think about it a lot of times, but sometimes we're only putting a 0 in there because we need it to like represent where we are in our number scale, what value of 10, like we saw in our scientific notation, we're at. Significant figures tell us the range of values to expect for repeated measurements. Okay, so that means that if we consider the lowest value that could be represented by a significant, by a number. So we take our significant figures, we imagine what the lowest value that it could be if we went on the low end of that estimated value, and the top end of it, okay, if that estimated value was at its highest, that would still get us that significant figure. That means that our repeated measurements should fall between that top and bottom range. The more significant figures there are in a measurement, therefore, the smaller the range of values. Therefore, the measurement is more precise. So if we know a whole bunch of digits and we know that the repeated measurements are only going to change in that last digit, then we're getting more and more precise measurements. Okay, we know with more and more certainty what those values are going to be. Okay, so let's look at some examples here. If we have 12.3 centimeters, this has 3 significant figures, and its ranges from 12.2 to 12.4. Okay, so if we do repeated measurements, we're always going to see values that should be between 12.2 and 12.4. Whereas if we rewrite this as 12.30 centimeters, we have 4 significant digits. And this means that we should now be seeing values that are between 12.29 and 12.31. So we can see that the more significant digits we add, the tighter the ranges on our measurements, and the more precisely we know what the true value is going to be. So let's talk about how we count significant figures. All non-zero digits are significant. Okay, so this is an important rule. So we don't need to quibble about numbers that aren't zeros. So really we just have to figure out when a 0 is significant and when it is not. All right, so an example of this is 1.5 has 2 significant digits, the 1 and the 5. Okay, so all interior zeros are significant. Now, what do we mean by an interior 0? We mean that this 0 here is between 2 non-zero numbers. Okay, so even if there was another 0 here, if there is a non-zero number to the right of any set of zeros and a non-zero number to the left of any set of zeros, all the zeros in between are significant. So any interior ones. Trailing zeros after the decimal point are significant, okay? And this is very important that we make this distinction of being after the decimal point, all right? So when we have decimals, if we have a 0 here at the end, that is significant. And if you think about it, right, Why would I have even wrote that 0 there if I didn't mean to make it significant? I do not need this 0 here in order to write this number, right? I could write 1.05 and that would be a perfectly valid way of representing a number, okay? The fact that I went ahead and put that 0 at the end means that I intend for that to be one of the significant digits. All right, so leading zeros are not significant, okay? So by leading zeros, we mean these zeros that are at the beginning of the number. These are the leading zeros. This 0 here is an interior 0. This 0 here is a trailing 0. So our leading zeros here are not significant. And again, if we think about it, I need to write these in order to represent this number. Okay, there's no way for me to represent this number that isn't scientific notation without writing those numbers. Okay, so therefore, if these don't count, this has 4 significant figures: a 1, a 0, a 5, and a 0. Now, when I write this using scientific notation, I will only be writing the significant digits in the decimal place here. Okay, and that will always be true. These decimal values here are only the significant digits that you're going to write when you write these things in scientific notation. Okay, zeros at the end of a number without a written decimal point. Okay, so we've talked about the trailing zeros when we have the decimal place. Now we're talking about when we're writing without the decimal point, are ambiguous and should be avoided by using scientific notation. Okay? So what we're saying here is that this significant figures convention, as I've mentioned before, it's pretty lazy and there are some holes in it, okay? Probably something scientists need to fix eventually, but I guess they're working on other stuff. So if we have the number 150, this could have 2 significant digits, meaning the 1 and 5 are the only significant ones and 0 is an estimate. Or it could have 3 significant digits, meaning that 1, 5, and 0 are all significant. All right. So it could either be 1.5 times 10 to the 2, okay? Or if it was 3 significant digits, then it could be 1.50 times 10 to the 2. Now, one way of working around this, okay, that is consistent with everything else that we've said, but not fully adopted yet, is to write out a number like this when you intend for it to have 3 significant digits. So you would write 150 and then you'd place a decimal place here, okay, and that would indicate that this 0 here is significant, okay, whereas if we wrote it like 150, we would be saying that this 0 is not significant. All right, but that has not been completely adopted yet, so we cannot trust that when somebody writes 150, they could be using this scheme, or they could not even know about that. We're not really sure when we're doing that, okay? But this is something that has been added in order to work around this problem of ambiguity with the significant figures convention. So exact numbers have an unlimited number of significant figures. All right, remember we were talking about exact numbers versus measurements before. When you have exact numbers, they are unlimited in the number of significant figures that they have. A number whose quantity is known with complete certainty is exact, from counting individual objects and from definitions. So we talked about how we're going to get those. All right. 1 centimeter is exactly equal to 0.01 meters. This is an example of a definition, okay? And the integer values that you're going to, an example of this is going to be the integer values that you see in equations. For instance, the equation of the radius of a circle, we have that the radius of a circle is equal to the diameter of a circle divided by 2. Now this is, again, a confusing thing, okay? Because we're just writing a 2 here. And if it was a measurement, that would say that we would have 1 significant figure here, right? Now, we know that this has an unlimited number of significant figures. So if you think about how I would write this by defining that it had an unlimited number of significant figures using our convention, I would write 2.0000000 going on forever and ever and ever, right? And we'll see in a second that what I would really need to do is write enough zeros to at least over, or to be at least have more significant figures than either of these two measurements. All right. But I would be writing these all out. They don't do that. They're lazy. They just write it as a 2. And you have to recognize that this is an exact number and that you're going to take it to have as many significant figures as it needs, as opposed to a measurement. So let's take a look at an example here. How many significant figures are in each of the following numbers? So if we have 0.0035, we have our leading zeros here that are not significant, and we have our two significant values, 3 and 5. If we have 1.080, we have interior zeros that are significant and a trailing zero after the decimal place that is also significant. So we get 4 significant figures for that value. For 2371 here, 2371, we have all non-zero integers. Therefore, all of them are significant. We have 4 significant figures. For 2.97 times 10 to the 5th, we know that when we write things in scientific notation, we're only writing the significant figures here in the decimal portion. So this is going to be 3 significant figures. And for 1 dozen is equal to 12, we know that this is a definition. Therefore, these are exact numbers, and they're going to have an unlimited amount of significant figures. When we write out 100,000, we know that that is ambiguous. Okay, we do not know exactly how many significant figures this number has, because it has, it's leading all the way up this. Now, if this was a 1, all of these zeros would be interior, and then we would know, right? So it's only the case when we're ending a number without a decimal place. We never write a decimal place with all zeros. We do not know which of those zeros are ambiguous, are significant, and which are not. Determine the number of significant figures, the expected range of precision, and indicate the last significant figure for each of these guys. So I'll give you guys a second to work on those. You can pause the video. So if we take a look at this, we had 12,000. This means that we have 2 significant figures, right? If we're taking it to be kind of ambiguous, we're going to take the least number of significant figures for this. So if you're asked and really pressed to do one of these ambiguous ones, you're going to give it the least number of significant figures that you can. And we know that this value should be somewhere between 11,000 and 13,000. Again, if we end it with a decimal place here, we will say that this last one here alone is the one that is uncertain, and we can say that this is between 119 and 121. If we hadn't written that, we really wouldn't know. We'd have to go up to here and say that the value is somewhere between 110 and 130. When we have 12.00, we can say that this last one here is the ambiguous one. We get our range there, and we can do the same thing here. Again, we know that all of these are significant, so whenever we're doing scientific notation, it will always be that last digit that we're talking about. Here we can see that this is this is the last significant digit here. We know that these are not significant digits, but these non-zero ones are. We know that the trailing zero in a decimal place is a significant digit, so we'll go to that place there. Here we don't really have an issue with an interior 0. We know that as soon as we have numbers on either side of it, that means that all of these are significant. We'll go to the last one. And then again here, we're into our ambiguity phase here where we're not sure where this is. We'll take it to be the least one here, our non-zero value that is furthest to the right, and then we will develop our range from that. So now we need to talk about how we're going to do math with significant figures. And this is a very confusing thing for students when they first start off, because you wind up writing mathematical statements that are not strictly true as you wrote them when you were in math class. So let's talk about what exactly I mean by that. So when you're multiplying or dividing measurements with significant figures, the result has the same number of significant figures as the measurement with the fewest number of significant figures. So there's a lot there to unpack. Let's take a look at an example. All right, so if I have 5.02 times 89,665 times 0.10, if I type this into the calculator like I would have been during math class, I would get 45.0118, okay? But when I'm using my significant figures convention, what winds up happening is I have to figure out the number of significant figures in each one of these, and whichever one has the lowest is going to limit what my answer can have for significant figures, okay? So 5.02 has 3 sig figs, 89,665 has 5 sig figs, 0.10 has 2 sig figs. This means that the lowest one is 2 sig figs. My answer needs to be limited to 2 sig figs. So when I write this out in science class, I'm going to write that this times this times this is equal to 45, okay? Not 45.0118, all right? And that way I'm maintaining that with the uncertainty of these values, I know that the answer here is going to be between 44 and 46. That's what I'm writing when I mean this, okay? And you'll notice that the true value you would have gotten is also between 44 and 46. If I take a look at this example, you guys can see I have 1, 2, 3, 4 sig figs here, right? I have 3 here because my trailing 0 is significant. If I type that into the calculator using division this time, right, I would get this value here. But again, because I'm limited to just 3 sig figs from this value here, I can only write my answer with 3 sig figs over here. And in this case, I wound up having to do some rounding where I rounded up from this value here, which we will talk about shortly. So here's our rounding. When rounding to the correct number of significant figures, if the number after the place of the last significant figure is 0 to 4, we're going to round down. Okay, so we're going to go to the last significant figure that we have. We're going to look at the number next to it. If that is a 0, a 1, a 2, or a 3, or a 4, we round down. Okay, when we're going to drop all the rest of the digits after that. If our number is 5 to 9, we're going to round up. Okay, we're going to drop all the digits after the last significant figure and increase the last significant figure by 1. All right, we'll add any insignificant zeros that we need to make this all work out in the end. All right, so let's take a look at some examples of rounding. Okay, so if we want to round a number, this number to 2 significant digits, right? We're going to take a look at this. We're going to say 1, 2, 3. There's 3 significant digits here. I want to round it to 2 sig figs. I've got 1, 2. So I want to round this value, right? What do? I look at the next neighbor to the right of it, and I say that's a 4. Because that is 0 to 4, I'm going to round it down, and I'm going to get 2.3. if I had a number like this, 2.37, and I want to round this to 2 significant digits, I'm going to go to the one I want to round. I'm going to look at its neighbor to the right. I'm going to say, well, that one's 5 to 9. Therefore, I'm going to round it up. And I'm going to make this 3 into a 4. Now, sometimes we have extra digits past the point that we want to round it to. So if we want to round this to 2 sig figs, it's the exact same here. So we got 1, 2. I need to look at this neighbor right here, and I am going to ignore all the rest of these numbers. It does not matter what those numbers are at all. It's just like this example up here. Okay, I'm going to look at the 4. I'm going to say that rounds down, and I'm going to rewrite the number as 2.3. Okay, so do not be swayed if there's other numbers here. You look to its immediate neighbor to the right. If we have a decimal value here, and we want to round that to 2 sig figs, well, then we need to look and find out where our first two most leftmost sig figs are. Okay, so this isn't significant. This isn't significant. This is our first sig fig. This is our second sig fig. So we're still rounding to this 3 here. And we still go and look to its immediate neighbor, this 4. All right. And we still round down by truncating it and getting rid of any numbers past it. All right. And we could come up with 0.023. If we rewrote this in scientific notation, again, we're only going to write our significant values here in this decimal, and we're going to have our exponent part there that tells us where we're going to place that decimal place. Again, if we're looking at this, we're going to ignore these insignificant numbers here. We're going to 1, 2, because we want to have 2 sig figs in our final answer. We're going to look at this 7. We're going to round that up, and we would write it with scientific notation like this. And again, it does not matter what other values we have at the end. We're going to ignore those, and we're only going to look at the immediate right neighbor to the one that we want to round, the place that we want to round to. If we had larger numbers that we wanted to round, like this, again, this is just going to become 230, and we'd write the scientific notation like that. If we were rounding it up, we could write 240, or 2.4 times 10 to the 2. And again, we will not let it be swayed by the fact that there are numbers past this. We're just going to go 1, 2 significant digits. We're going to look to the immediate neighbor. We're going to ignore the rest of these numbers. We're going to cut those off in the end to round down, and we will write the scientific notation like that. Okay, so determine the correct number of significant figures for each calculation and round and report the results. So this is question number 1 here. So we have 1.01 times 0.12 times 53.51 divided by 96 is equal to 0.067556. And we have 56.55 times 0.920 divided by 34.2585 is equal to 1.51863. These are the values that we would get from the calculator. I want you guys to do the calculations using the significant figures convention and tell me, how do we round these final numbers? You can pause the video and take a moment to do that. All right, so if we take a look at the results here, we had 3, 2, 4, and 2 significant figures. We know that we're limited by these 2 significant figures here. Our final answer should have 2 significant figures. We know that these leading zeros are not significant, so we're going to start here, 1, 2, and we're going to round to this value. We look at the 5, and we say we got to round up here. This value is 0.068. Again, here we had 4, 3, and 6 significant figures in our values. We know we're limited by this 3. We come over here, 1 sig fig, 2 sig figs, 3 sig figs. Again, we look to its immediate neighbor. That's an 8. We need to round up. This value is 1.52. So we've handled addition and or multiplication and division with sig figs. It's actually a little trickier to do the addition and subtraction with sig figs. So let's talk about what exactly we're going to do here. So when adding or subtracting measurements with significant figures, the result has the same number of decimal places as the measurement with the fewest number of decimal places. Okay? So now we need to think about our decimal places. All right? So we are not going to write a number that has any more decimal places than the one that has the fewest number. So this one has 2 decimal places. This is different than sig figs. This is 3 sig figs with only 2 decimal places, right? This has 3 decimal places. This has 4 sig figs but 3 decimal places, okay? We're limited to the least number of decimal places. That means that we're going to have a 2 here, all right? That means that our answer, however many sig figs it has, is only going to be able to have 2 decimal places, all right? So if we type this all in the calculator, we would get 9.214, but we only get 2 decimal places, so the number becomes 9.21, all right? When we're doing subtraction, we have the same thing here. We only get 1 decimal place in this case. Our number comes out as 0.835. So we go to our 8 here. We're going to round that number down because this is a 3. This number is actually only 0.8 at this point. I'll give you guys an opportunity to try these and to round these final values to their correct number of decimal places. So if we look at the results for this one, we start off over here. This has 1 decimal place. This is our limiting guy, right? We got 3 and 2 here. We're going to be limited by 1 decimal place. We go to that first decimal place. We look to its immediate neighbor to the right. We say that's a 6. I'm rounding up. I get 204 or 124.9. And then if we take a look at this guy down here, we've got 2 decimal places here. That means that I'm only going to get to be able to have 2 decimal places here. I go to that second decimal place. I look to its immediate neighbor. That's a 4. I'm going to be rounding down. I get negative 8.66.